Hello everyone. Today I'll be giving a quick breakdown of SVD, or singular value decomposition. So to begin, SVD can be applied to any matrix that is n by n, right? So this can be applied to any matrix, and it is the best and most factored any matrix can be. So before we learned about like QR factorization or like diagonalization, right? But those only apply to certain types of matrices, like square matrices, as well as having the criterion of being diagonalizable to begin with. But the most powerful aspect of SVD is that we can use it to factor any type of matrix, any n by n matrix, right? And A is factored into the form U times sigma times V transposed. So here, both U and V transposed are orthogonal matrices. So that means that the columns of the matrix are all normalized, right? So they all have magnitudes of 1, and they're all orthogonal to each other. So they're all perpendicular to each other. And then sigma is a diagonal matrix. And another important thing is noting the dimensions of U, sigma, and V transposed. So for any n by n matrix A, U has to be n by m, sigma has to be n by n, and then V transpose has to be n by n. And this is actually very useful, and we will be using the dimensions to figure out some of the matrices, and we'll be using it to help us as a tool to find U, sigma, and V transposed. Okay, so that being said, let's go through the basic steps on how we can find the SVD of matrix A. So, and I will be working this out as well, so you'll be able to see it as an example. So the first step is to compute A transpose A. And A transpose A is a symmetric matrix, so that just means that the transpose of A transpose A is equal to A transpose A. And after we find A transpose A, we need to find the eigenvalues and eigenvectors of A transpose A. And through this, we can construct the matrix x1 dot 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 xn. So the matrix containing the eigenvectors as the columns transposed is equal to V transposed. And after that, we will be solving for sigma I, which is equal to the square root of the eigenvalues, right? And through sigma I, we can find ui, which is equal to 1 over sigma I times A times vi. And ui is basically the column vectors of the matrix U, and we can find the column vectors through the formula. And again, I'll work through an example, so it will be a lot more clear after that. And depending on the matrix A, right, we will have to find U3, and we can do this through through cross products. And then finally, we can find sigma through using the formula. The matrix sigma is equal to D surrounded by zeros, where D is the matrix composed of the square roots of the eigenvalues along the main diagonal. So again, D is very similar to the diagonal matrix that we solve for when we diagonalize a matrix. Only instead of having just the eigenvalues, it's the square root of the eigenvalues. Okay, so with this, let's go ahead and solve an example problem. So I'm gonna go ahead and move this over there so we have more space to work with. So I'm also gonna put the dimensions up here. Yeah, so A, n by n, U is n by m, sigma is n by n, and then finally V transpose is n by n. Okay, and I'm also gonna erase, actually we can just keep that here, this is fine. Okay, so for the example problem, let's find the SVD decomposition of A, where A is equal to 1, 1, 0, 1, negative 1, 1, right? Okay, so let's go ahead and put our answer over here. So A, as we can see from the given matrix, A is a 3 by 2 matrix. So that means that U will be a 3×3 matrix. Sigma will be 3×2. And then finally, V transposed will be 2×2. Okay, so first up, let's find A transpose A, right? So A transpose A is essentially just the inner product. Let's go ahead and just write that out. So A transpose A is simply just 1, 0, -1, 1, 1, 1. A is 1, 1, 0, 1, -1, 1. So let's go ahead and compute this, right? So that's 1, 0, 1, that's 2. That's 1, 0, -1, so that's 0. And then this is supposed to be 0 because, again, this is a symmetric matrix, right? And then finally, we have 1 times 1 is 1, 1 times 1, 1, 1 times 1, 1. So that's 3. Okay, so this is A transpose A. So yeah, we're done with the first step. Now we need to find the eigenvalues and eigenvectors of A transpose A. So we can use the property of trace and determinant, right? So we know that lambda1 plus lambda2 is equal to the trace, which is the sum of the entries along the main diagonal, so that's just equal to 2 plus 3 equals 5. And we know that lambda1 times lambda2 is equal to the determinant of 2, 0, 0, 3, which is just equal to 2 times 3 minus 0 times 0 equals 6. So the sum is equal to 5, the product is equal to 6, therefore lambda1 is equal to 3, and lambda2 is equal to 2. Okay, so, and it doesn't really matter what order you have the eigenvalues in, just make sure that you keep track of them and keep them in the same order so that when you're finding the eigenvectors, that they don't get mixed up, and when you're constructing the matrix D. Okay, so now let's find the eigenvectors. So for lambda1 is equal to 3, we can just use the formula that lambda I minus A times X is equal to 0. So here we have 3 times the identity matrix, that's 3, 0, 0, 3, minus we have 2, 0, 0, 3, that's equal to 1, 0, 0, 0. And we can multiply that by x1, x2 is equal to 0, 0. From the first one, we have 1 times x1 plus 0 times x2 is equal to 0. So therefore, x1 has to equal 0. And we can find simply x2 is equal to 1 for the simplest eigenvector, and this will give us 0, 1. And then next, we have lambda2 is equal to 2. So here we have lambda I minus A times X is equal to 0. So here we have 2, 0, 0, 2. Again, just 2 times the identity matrix minus, let's see here, 2, 0, 0, 3. So this is equal to 0, 0, 0, -1. x1, x2 is equal to 0, 0. Okay, and again, from the second one, we have 0 times x1 minus x2 is equal to 0, so therefore x2 has to equal 0. And then we just choose x1 to equal 1. So we have here that the first eigenvector is equal to 0, 1. The second eigenvector is equal to 1, 0. And now we can construct VT, right? So V transpose is simply just the matrix composing of the eigenvectors 0, 1, 1, 0. Transposed would give us the same 0, 1, 1, 0. So now we've found V transpose, right? Okay. And our next step is to find sigma, right? So we can use this formula that sigma I is equal to the square root of lambda I. Let me go ahead and erase this. So here are our two eigenvalues, right? So sigma I is equal to square root of, or sigma 1 is equal to square root of 3. Sigma 2 is equal to square root of 2. Okay, so now we can find u1. u1 is equal to 1 over square root of 3 times a. And then finally, v1, right? And v1 is just the first entry on v transpose, so that's just 0, 1. And then u2 is equal to 1 over square root of 2 times a, and then times second entry, 1, 0. Okay, and we can go ahead and compute this, right? So this is just equal to 1 over square root of 3 times, that's 1, that's 1, that's 1. And this is equal to 1 over square root of 2 times 1, 0, negative 1. Okay, and so again, if we look over here, we see that U has to be a 3 by 3 matrix, right? And we found the first two column vectors of U, so now we have to find the third one. But conveniently, again, remember that U and V transpose are both orthogonal matrices, right? So therefore, we know that U3 has to be orthogonal to U2, has to be orthogonal to U1, right? And we can simply use the cross product to solve for U3. So we know that U2 cross U1 is orthogonal to U2, orthogonal to U1. So therefore, we can have U3 is equal to U2 cross U1, and we can compute it in the following way. So U3, right, I, J, K, we put U1 in first. So let's just simplify calculations and leave the vector without the 1 over square root of 3. And similarly, we have 1, 0, negative 1, right? So this is just equal to 1, 1, 0, negative 1, I minus 1, 1, 1, negative 1, J plus 1, 1, 1, 0, K. Okay, and this is equal to negative I minus negative 2J plus negative K. So this is just equal to the vector negative 1 to negative 1. Okay, and U1 and U2, they're already normalized, as we can tell, with the magnitude of this vector equal to square root of 3, and then we divide by square root of 3 here. And similarly, the magnitude of this vector is square root of 2, and we've already divided by square root of 2. So now we just need to normalize the vector U3. Now, the magnitude of U3 is square root of negative 1 squared plus 2 squared plus negative 1 squared, which is equal to square root of 6. So we just multiply by square root of 6 here to normalize it. And yeah, so now we have found U1, U2, U3, so we can go ahead and construct U over here, right? So U1 is just 1 over square root of 3 times 1, so we can go ahead and rationalize that as square root of 3 over 3, square root of 3 over 3, square root of 3 over 3, right? U2, we have square root of 2 over 2, 0, negative square root of 2 over 2, and then finally, U3, we have negative square root of 6 over 6, square root of 6 over 3, negative square root of 6 over 6. And then finally for sigma, we can simply just take D. D is equal to, we have lambda 1 is equal to 3, lambda 2 equals 2, so this is just equal to square root of 3, square root of 2, 0, 0. And finally, since sigma has the dimensions 3 by 2, right? So we can go ahead and fill in zeros so that the dimensions match. And we can fill in 2 zeros at the bottom so that we have square root of 3, 0, 0, square root of 2, 0, 0. And just like that, we have completed the SVD factorization of A. So that matrix 1, 1, 0, 1, negative 1, 1 is equal to the following product. Thank you very much.